Hi, I am Eric Pınar and I am the member of the group 32. As a group, we have designed EMI filter for DC-DC converters. As you can see here, these are the roles we had during the project. First of all, what is EMI? Electromagnetic interference is the interference caused by an electromagnetic disturbance that affects the performance of a device. It often manifests as undesirable noise, and it has four types: conducted EMI, common mode EMI, differential mode EMI, and radiated EMI. In details, electronic systems are sensitive to EMI, and it can cause distortions, data losses, and even total failure in various sectors. So we need the effective and low-cost solutions to reduce EMI. The EMI filter must limit conducted and radiated interference under some standard limits, such as mil-STD. And it should be compact, cost-effective, and work in the target frequency range. The design must also be safe, reliable, and thermally stable. So, why did we choose the EMI filter for reduced EMI? Because it has an effective frequency selectivity and it has a low cost and simple to implementation, customized solutions such as different topics and variety of filter options.
Hi, I'm Burcu Özdeşamış and I will be presenting the design and implementation phase of our project. To begin with, let me introduce the filter topology we selected. In general, there are two main types of electromagnetic noise, common mode and differential mode noises. In our design, we chose a topology that can suppress both types of noise. Of our output stage is based on a buck converter with 28 volts inputs and 12 volts output. Here you can see the unfiltered version of our circuit simulated in LT Spice. In the CE102 standard, measurements are taken from positive and negative terminals through a line impedance stabilization network. So we included the Lism model in our simulation, and you can see our buck converter with this Lism integrated. And in the unfiltered configuration, FFT measurements showed noise levels exceeding CE102 limits. Based on this data, we identified the necessary cutoff frequencies and designed an EMI filter accordingly. And here you can see with the design filter added with the Lising connection, and here measurement results show that our filter successfully reduced the noise within CE102 limits. And once the filter performance was verified, we went to component selection and began PCB design using Altium Designer. And this slide shows schematic diagram at the PCB layout of our final design. After PCB was fabricated, we continued with the assembly process. First assembly components were applied using solder paste and reflow soldered in an oven. Then through-hole components were mounted using manual soldering techniques. After all, we are assembling a 28-volt input was applied, and we successfully observed 12 volts outputs, confirming that the buck converter was operating correctly. Finally, circuits was wired and prepared for C102 testing, marking the transition to measurement phase.
Hello, I am Nihal and I am the team leader in project. In this part of presentation, I will talk about the testing process of our filter. We use military standard 461G. It's a testing standard for electromagnetic interference, which covers four main titles: conducted and radiated, emissions and susceptibilities. We examined CE102. It's a test applied for conducted emissions transmitted through power cables within the frequency range of 10 kHz to 10 MHz. This test includes predefined limit levels for EMI emissions. To carry out the test properly, we use line impedance stabilization network. It filters external electromagnetic noise, allowing us to obtain clean and accurate measurements from our own EMI filter. Here we see the test setup from the standard itself. Before actual testing, we run simulations using LT-SPICE. The simulation helped us to predict the expected behavior of the filter before producing it and before moving on to the actual testing. We didn't just design the EMI filter, we also developed and produced it. After manufacturing the PCB, we created proper cabling for actual test. Here is the noise without the filter. It has peak points in the harmonics of our converter switching frequency, as seen in here. And here is the noise with the filter. As shown in the test results, there is a clear difference between the system with and without the EMI filter. Our filter successfully reduced the conducted noise and ensured that DC-DC converter meets the required EMI performance.
My name is Emre Deveci and I will talk about cost analysis and commercialization. This is our bill of material list and it includes details about description, design and manufacturer, quantity and unit price per PCB. Updated commercialization plan. After evaluating the MI filter, we made updates to our initial commercialization plan. Target application. The filter is designed for DC-DC converters and is suitable for use in industrial control systems and IoT devices. Production approach. In the early stages, production will be done externally in small batches. However, we consider assembling in PCBs in-house after pilot phase to reduce long-term costs. Cost efficiency. When we move to larger scale production, we plan to use custom-made inductors in bulk to reduce unit costs. Sales and distribution. We plan to sell the product through electronics distributors and online platforms commonly used in Turkey. Standardization and certification. The MI filter and buck converter module were developed in compliance with the military standard 461G CE 102 test standard, which evaluates conducted emissions in the 10 kHz to 10 MHz frequency range. All components were selected based on industry standards and met military grade specifications. Safety aspects. The circuit is designed with a strong emphasis on electrical and thermal safety. All components operate well below their maximum rated values, minimizing the risk of electrical failure. Diodes and capacitors are integrated to protect against overvoltage conditions and transient spikes. The system was tested at full load with all components operating safely, and the 95% efficiency kept thermal losses to a minimum. ESD wrist straps was used to protect against electrostatic discharge. Thank you for listening to us. For any further question, you can email to us.